The overall goal of the following experiment is to conduct a Miller-Urey spark discharge experiment. This is achieved by placing water into a reaction flask to represent the early Earth's oceans. As a second step, a suite of gases is introduced into the reaction flask to mimic primitive atmospheric conditions. Next, an electric discharge is applied within the reaction flask in order to imitate lightning on the primordial Earth. Results are obtained that show molecules important for life can be detected based on high-performance liquid chromatography with fluorescence detection amino acid analysis of spark discharge samples.
The Miller-Urey experiment can help answer key questions in the origins of life field, such as which types of prebiotic conditions may have facilitated the synthesis of specific organic compounds believed to be important for life.
To begin this procedure, set up the manifold and vacuum system as described in the text protocol. Pour 200 milliliters of ultrapure water into a 3-liter reaction flask. Introduce a pre-cleaned and sterilized magnetic stir bar which will ensure rapid dissolution of soluble gases and mixing of reactants during the experiment. Attach the tungsten electrodes to the 3-liter reaction flask using a minimal amount of vacuum grease, with tips separated by approximately 1 centimeter inside the flask. Fasten with clips. Insert an adapter with a built-in stopcock into the neck of the 3-liter reaction flask and secure with a clip. Attach the 3-liter reaction flask to the gas manifold via the adapter. Use a clip or clamp to help secure the flask. Open all valves except valve 6 and stopcock 2 on the manifold, while leaving all stopcocks attached to the reaction flask closed. Turn on the vacuum pump to evacuate the manifold. Once a stable vacuum reading of less than 1 millimeter of mercury has been attained, close valve 1 and allow the manifold to sit for approximately 15 minutes to check for vacuum leaks. After 15 minutes, apply magnetic stirring to the reaction vessel. Open valve 1 and stopcock 1 to evacuate the headspace of the 3-liter reaction flask until the pressure has reached less than 1 millimeter of mercury. Calculate the necessary pressure of gaseous ammonia to introduce into the manifold as described in the text protocol. Ensure valve 6 is closed and close valve 1 and any stopcocks attached to the reaction flask while leaving stopcock 2 open before introducing any gas into the manifold. Introduce ammonia into the manifold to reach the determined pressure. Open stopcock 1 to introduce 200 millimeters of mercury of ammonia into the 3-liter reaction flask. The ammonia will dissolve in the water in the reaction flask and the pressure will fall slowly. Once the pressure stops dropping, close stopcock 1 and record the pressure read by the manometer. This value represents the pressure inside the flask and will be used to calculate the pressures for other gases that will be introduced into the manifold later. Open valve 1 to evacuate the manifold to a pressure of less than 1 millimeter of mercury. Close valve 2 and disconnect the ammonia gas cylinder from the manifold. After calculating the necessary pressure of methane to be introduced into the manifold as described in the text protocol, ensure valve 6 and all stopcocks attached to the reaction flask are closed, while having all other valves and stopcock 2 open to evacuate the manifold to a pressure of less than 1 millimeter of mercury. Close valve 1 once the manifold has been evacuated. Introduce methane into the manifold until the calculated pressure is reached. Then, open stopcock 1 to introduce 200 millimeters of mercury of methane into the 3-liter reaction flask. Close stopcock 1 once the intended pressure of methane has been introduced into the 3-liter reaction flask and record the pressure measured by the manometer. Open valve 1 to evacuate the manifold to less than 1 mm of mercury. Finally, close valve 2 and disconnect the methane cylinder from the manifold. Ensure valve 6 and all stopcocks attached to the reaction flask are closed, while having all other valves and stopcock 2 open. Evacuate the manifold to a pressure of less than 1 mm of mercury. Close valve 1 once the manifold has been evacuated. Introduce nitrogen gas into the manifold until the calculated pressure is reached. At this point, open stopcock 1 to introduce 100 mm of mercury of nitrogen gas into the reaction flask. Close stopcock 1 once the intended pressure of nitrogen gas has been introduced into the reaction flask, and record the pressure using the manometer. Open valve 1 to evacuate the manifold to less than 1 mm of mercury. Close valve 2 and disconnect the nitrogen gas cylinder from the manifold. Detach the reaction flask from the manifold by closing stopcock 1 and valve 1 once all gases have been introduced into the reaction flask. Then open valve 6 so that ambient air may enter the manifold and bring the manifold up to ambient pressure. Secure the Tesla coil connected to the high-frequency spark generator. Connect the opposite tungsten electrode to an electrical ground to enable the efficient passage of electrical current across the gap between the two electrodes. Set the output voltage of the spark generator to approximately 30,000 volts, as detailed by documents available from the manufacturer. Prior to initiating the spark, close the fume hood sash to serve as a safety shield between the apparatus and the experimenter. Turn the Tesla coil on to start the experiment, and allow sparking to continue for 2 weeks in 1-hour on-off cycles. Stop the experiment by turning off the Tesla coil. Open stopcock 1 to slowly introduce ambient air into the reaction flask and facilitate the removal of the adapter and the tungsten electrodes so samples can be collected. If desired, a vacuum can be used to evacuate the reaction flask of noxious reaction gases. Using a pyrolyzed glass pipette, remove liquid samples from the reaction flask, being careful to minimize exposure to contaminants, such as those that might be introduced by touching the pipette to the vacuum grease or other non-sterile surfaces. Transfer the sample to a sterile plastic or glass receptacle. Seal sample containers and store in a freezer capable of reaching temperatures of -20 degrees Celsius or lower, as insoluble products may prevent the sample solution from freezing at 0 degrees Celsius. Use clean laboratory wipes to remove vacuum grease from the neck of the apparatus, the adapter and stopcock, and the glass surrounding the tungsten electrodes. Thoroughly clean these same surfaces with toluene to fully remove organic vacuum grease from the glassware. If using silicone grease, the high vacuum grease may remain on the glassware after pyrolysis, creating future problems as detailed in the text protocol. Then, thoroughly clean the reaction flask with a brush and the solvents listed in the text protocol in the order listed there. Cover all open orifices of the reaction flask with aluminum foil and wrap the adapter and its components in aluminum foil. Once all the glassware has been wrapped in aluminum foil, pyrolyze for at least 3 hours in air at 500 degrees Celsius. Finally, gently clean electrodes with methanol and let air dry. Proceed to analyze the samples as described in the text protocol. Shown here is a chromatogram of an O-ethyldialdehyde, N-acetyl L-cysteine, or OPA-NAC derivatized amino acid standard obtained by HPLC coupled to fluorescence detection and triple quadrupole mass spectrometry. The amino acids contained in the standard include those typically produced in Miller-Urey type spark discharge experiments. Representative fluorescence traces of a typical sample and analytical blank are shown, demonstrating the molecular complexity of Miller-Urey type electric discharge samples. This sample chromatogram was produced from a spark discharge experiment using 300 millimeters of mercury of methane, 250 millimeters of mercury of ammonia, and 250 milliliters of water as starting conditions.
After watching this video, you should have a good understanding of how to conduct a Miller-Urey spark discharge experiment.